Good morning to all of you. I hope I'm audible.
Yeah, sir. Good morning.
Good morning, sir.
Okay, I hope you can see the shared screen.
No, sir.
Is it visible now? I hope now you can see the screen.
Yes, sir.
Yes, sir.
Okay, fine. So in the previous lectures, we discussed about fundamentals and basics of remote sensing. Okay, and in the previous talk, we had discussion on energy sources, okay, and different radiation principles. Fine. And before that, in one of the lecture, we discussed about what are the steps which are followed for geo-information acquisition. Okay. So there we discussed about sun is as energy source, then the radiation which comes from sun that passes through the earth atmosphere. Okay. So it enters in the earth atmosphere, then finally reaches to the ground surface object. Then at the ground surface, what happens? That there are two phenomena. The first one is energy is reflected back, okay, and remaining part of energy is either transmitted or it is absorbed. Okay. So now we discuss this in more detail, like when the energy component interact with the Earth surface object over here. Okay. So the law of energy, the law of conservation of energy is applicable over here. So let's say if the total energy that is falling on this, let's say point A, we consider a pointed area over here. This is a total incident energy EI. Okay. Then part of energy is reflected back. Okay. While interacting to the bulk material, the part of energy is absorbed. We write it EA. Okay. Then further, the remaining energy that is transmitted into the second medium from the first. So we can write it energy equation over here, where the total incident energy EI is equal to the radiated component, sorry, the reflected component plus absorbed component plus transmitted component. Okay. Now, when we see the different medium through which energy propagates, okay, so if we consider the solid medium, solid material on the Earth's surface like trees, building, uh, bare ground, grass field, forest land, okay. So in that case, what happens when from those particular object, this energy EI interact, fine. So in that case, we can say that it's solid medium, okay. So in the solid medium, we can say this transmitted energy is approximately 0, because we can expect the transmitted energy component only in case of either the second medium is air or it is liquid. Is it okay? So if this is a bulk solid material at point A, if we consider it, then the transmitted component is approximately 0. Then what we have? We have the EI, incident energy. It will be equal to now the reflected plus absorbed. See, this discussion I am keeping in the context of the radiation law, which we discussed in the previous lecture. Okay, where we talk about if temperature of a particular material T is greater than 0 degree Kelvin, then what happens in that case? Who will tell me? Tell me, if material temperature is greater than 0 degree Kelvin, what will happen in that case?
Sir, it will emit energy from itself also.
Okay, so which radiation law apply over here?
Sir, M equal to sigma T to power 4.
Yes, correct. So the M is equal to sigma T to the power 4. It is Stephen Boltzmann law. And if we write over here, that is M is equal to sigma T to the power 4. Okay. So this formula is valid for the black body, though Earth surface materials are the gray body, but still M is equal to sigma T to the power 4, where M is total radiant exitance from the surface of material. Okay, so M is total radiant exitance from the surface of material. It is measured in watt per meter square. Fine, as we discussed before. Now the sigma over here, it is a constant. We call it a Stephen Boltzmann constant, and its value is 5.6697 into 10 to the power minus 8, and it is again, the unit is watt per meter square. Okay, now T is considered over here the absolute temperature measured in degree Kelvin for the emitting material. Fine, the material that emits the energy. Now in this case, when the temperature, if let's say T is greater than 0 degree Kelvin, then you can expect a definite value for M, that is total radiant exitance. Okay, so if T is greater than 0 degree Kelvin, you can expect the value over here. Now again, we are coming back to the discussion at point A, considering this first equation. Okay, so from equation first, if I write over here, what is role of absorbed component over here? ER is the radiated component, sorry, this reflected component. Okay, and EA is the absorbed component at point A. What is role of EA over here? What will happen if material absorb the energy? Again, this is question for you. We have already enough discussion on this.
So surface temperature of the material will increase.
Obviously, see, I have already discussed over here law of conservation of energy. What it tells, the energy is constant, but just it change its form. So energy is converted from one form to another form, but it is constant. So what happened when the solid material like trees, building, etc., when they trap, when they absorbed energy EA, what will happen? It will be dissipated, and further it will be responsible for rise of temperature of that material. Okay, and overall, when you consider uh, this particular law of conservation of energy, as well as the total amount of radiation which is coming, which are interacting with the Earth's surface material, so on an average, what will happen? We consider the surface temperature of Earth as 300 degree Kelvin. Okay, so 300 is considered as surface temperature of Earth. It's average temperature. Okay, and why it is 300? What is the mechanism through which it raised to 300 degree Kelvin? It is due to the absorbed component over here. Fine. The reflected component is not responsible for this. Is it okay? Now again, one parameter also we need to incorporate over here. Till now we are not discussing the role of wavelength over here. And we know that wavelength affect the energy within the electromagnetic radiation. So at each wavelength, the energy component is different. Okay. So we can write this equation in the spectral form. It's we can say EI. Now it is the function of wavelength, and it is equal to the reflected component is the function of wavelength plus E A. Again, absorbed component is also the function of wavelength. Okay. So now this is the equation second, where we also considering the effect of wavelength in deciding this equation. Okay, it means this composition which we talk over here, EI is equal to reflected plus absorbed. Okay, this composition changes with respect to wavelength. Let's say if this is a 40% for one particular wavelength lambda 1, and this is the 60%. Okay, what will happen if, let's say, you change the wavelength and you just see this composition at lambda 2? So there is a possibility based on the characteristic of material, and that characteristic will change with respect to wavelength. It could be 30% and it further raised to 70%. Okay, and total there, total energy, that is 100%. I hope it is clear.
Yes, sir.
Okay. So I again revisit this discussion later on. So first, let me finish the radiation principles and energy source related discussion. And the objective behind this, to include this discussion prior, because this should come later on, is to just understand why the Earth temperature is 300 degree Kelvin. What is the responsible factor for that? Okay. So now if this is the query, it is very clear, like total energy that is interacting with the material EI is divided into two parts. In case of if the second medium is solid, so this formula apply using law of conservation of energy, and the incident energy is equal to reflected plus absorbed. And this absorbed component is responsible for rise of temperature of Earth's surface to 300 degree Kelvin. And at this value, 300 degree Kelvin, it is more than 0 degree Kelvin. Therefore, we have a value of M. Okay. I hope in synchronization with my discussion, you are also making note on this. I suggest you to sit with copy and pen and write it the way I'm writing on this virtual board. Fine.
हेलो सर.
Yeah, please.
सर ये रेडिएंट एनर्जी को जीरो क्यों ले लिया हमने, एक बार बता दीजिए.
Where I have taken 0?
Yes sir.
Where the radiant energy I have taken 0?
Sir, in first equation.
Okay, in first equation we have taken this transmitted component 0. See,
Okay.
in a simple example, if you have a laser light, okay, and if you switch on that, can that laser light pass through the wall?
No sir. No, sir.
Similarly, the light also can't pass or can't penetrate the solid material. Okay, and this ET is the transmitted energy component. If that electromagnetic energy within the electromagnetic spectrum, if that energy can't travel the solid medium, then obviously we don't have the transmitted component. Okay. We have
Okay,
the we have the transmitted component only. Let's say if this is the interface, and this is medium M1, and this is medium M2. Okay, and this is the energy source, and this energy source transmit energy component. It interact with this interface between medium M1 and M2. Then what will happen? We can expect a reflected component, and we can also expect a transmitted component, and some part of energy will be absorbed over here. Okay. So the transmitted component, when we can expect, when that energy has capability to travel in the medium without decay. Fine. If this is a air, if both medium M1 and M2 are air, then obviously in the air this electromagnetic radiation can travel. Okay. If this is a liquid, even in that case also it will travel, but at only at certain specific length. After that it will completely absorbed. So absorption length will be more in case of liquid. Okay, so in that length it will further travel, so we can see that we have a transmitted component. But if it is solid, where the molecules are very closely packed, so there is no void to allow the energy to pass through. Okay, so if the molecular composition is like that, they are tightly packed, so what will happen? That energy will not pass through. So we assume that the transmitted component is 0. But still, we have the absorbed component. This material will absorb the energy. Okay, and it will further, due to the absorption of energy, what will happen? We consider again this law of conservation of energy. It will rise the temperature of material. Okay, and in case of Earth's surface, the optimal temperature, the temperature at which it is settled, is 300 degree Kelvin. Okay, so this is the motive behind this discussion, why we consider that 300 degree Kelvin. Okay, and these are the fundamentals which are required to discuss this part. Okay, now again I'm coming back to the discussion of radiation principles. as well as a particular curve that we were discussing in the previous talk. So I would like to again draw that curve over here, or you can also access PPT that you have with you. Roughly, I will draw over here. So we have already discussed two radiation laws. The first one is the Stefan-Boltzmann law, which tells us m is equal to sigma T to the power 4. It means if the surface temperature of material is more than 0 degree Kelvin, in that case, it starts radiating the energy. Fine. First lies m is equal to sigma T to the power 4. Okay. While the second case, it is a Wien's displacement law, which tells us the wavelength at which material radiates the maximum energy. It is again inversely proportional to the temperature of the material. What it suggests? You see that equation I discussed, that is in the incident energy component vary with respect to wavelength. So this is equal to absorbed component plus reflected part. Okay. So this absorbed component varies with respect to change in wavelength. Okay. If it varies with respect to change in wavelength, it means what will happen? The rise of temperature is also varying with respect to wavelength. Okay. But we take on an average. Fine. So on an average, we consider it 300 degree Kelvin. So in that case, if we consider the 300 degree Kelvin for the Earth, so in this case, this Wien's displacement law, I expect you to calculate it. What is lambda m in case of Sun and what is lambda m in case of Earth? So calculate lambda m in case of Earth. What it will come? I hope you remember the constant A. The constant A is 2898 micrometer Kelvin. Okay. Micrometer Kelvin, it means the temperature is measured in Kelvin. And lambda m will come in micrometer. So in case of Earth, it is 300. Tell me what will the value of lambda m?
Nine point 66 micrometer.
9.46.
9.66.
0.6.
So if you are getting 9.66 micrometer, is it?
Yes, sir, 9.66.
You are getting 9.66 micrometer. So we can say that it is approximately, if we take one decimal place, so 9.7 micrometer. Fine. Now consider the second case. Is second, where you are going to measure lambda m for Sun. And in case of Sun, this temperature is 6000 degree Kelvin. Let me know.
Sir, 0.483.
0.483 micrometer.
Sir, 0.49.
0.483. How much you are getting? 0.48?
0.483.
0.483, sir.
Sir, 0.483.
Okay, so we can approximate, let's say 0.48, fine. .48 micrometer. What is implication of these two? Like lambda m, in case of Earth, we are getting 9.7. In case of Sun, we are getting 0.48. What does this mean? Can you see the correlation? Again, it will be discussed with respect to the curve I will plot. But could you see some symmetry over here? Symmetry is lambda m is inversely proportional to 1 by T. Okay, it means the temperature will increase, then lambda n will decrease. Okay, and it is justified over here. Like in case of 600 degree Kelvin, your wavelength is less compared to 9.7 micrometer. I'm plotting the spectral distribution of energy radiated from black body at the various temperature with respect to the wavelength. Okay, so this axis is on logarithmic scale, the dependent axis. Okay, so this is the wavelength. It is measured in micrometer. Fine. And on this axis, we have m lambda. Along the dependent axis, we have a lambda, and it is spectral radiant exitance now. Okay. Here, this is radiant exitance. Now it is spectral radiant exitance. It means how much amount of energy is radiated or transmitted from a material per unit area, per unit wavelength. So m lambda unit is in watt per meter square, that is amount of energy. Then it is it will be watt per meter square. The total amount of energy that is radiated per unit wavelength. Okay. Now we will plot the curve for sun as well as earth. Okay. So we have already using this Wien's displacement law, we have already calculated the wavelength at which the energy is maximum. It means at which wavelength m lambda is maximum. Okay. So in case of sun, we have already calculated it 0.48 micrometer. So it will lie somewhere here. Okay. So this is the point, this is the line. This line indicate 0.48 micrometer. This is the line of maximum energy. Okay. So this will be the peak. Now it is clear. Once you are going to plot the curve of m lambda with respect to wavelength, so peak you will get as 0.48 micrometer, and it is computed by Wien's displacement law. Fine. Now, if you refer the plot that we discussed even in the previous lecture, at 0.1, somewhere we have a 10.4 over here. It will start from here. It will be maximum over here. And further, okay, it means till 100 micrometer we can expect the m lambda value from sun. Okay, after 100 micrometer, the energy component in the radiation which is coming from sun is very low. So we have a significant energy component in the wavelength less than 100 micrometer. So there are many inference you can draw based on this plot to understand what kind of energy composition is there. Maximum you have in this band, let's say if we confine this, the visible spectrum, what will the range of visible spectrum? Who is going to tell me?
The 0.4 to 0.7 micrometer.
Yes, it will be. This is the band. Okay, and let's say this is 0.4 and this is 0.7. Okay, so within the visible spectrum, the energy radiated from sun is maximum. If we consider the wavelength before that and if we consider the wavelength after that. Okay, so this is one inference you can draw from here. Second inference, the first inference, the first conclusion was that we discussed previously, like if the wavelength is less than 100 micrometer, then the very low energy reaches to the Earth surface in that particular wavelength. Okay, now when we consider this second material, so it is sun where we consider temperature is 1000 degree Kelvin. Now coming back to the second case for the Earth surface, so temperature is, average temperature is 300 degree Kelvin, and in that case lambda is calculated 0.97. So you need to first fix the location of line. That line, equation of line, you write over here this lambda is equal to 9.7 micrometer. So this is the equation of line, and somewhere here we have a 9.7, and you can draw it. So lambda is equal to 9.7, equation of line, it is parallel to the m lambda axis. Correct? Now we'll see how the energy radiated from Earth varies with respect to temperature. Sorry, change in wavelength. Temperature is fixed, that is 300 Kelvin. So Earth starts radiating the energy at this particular junction over here. And I think this dividing line is 3 micrometer, is it? At 3 micrometer over here, this value is 3 micrometer. It will goes up maximum, then around 50 it will closes. Okay, so this is the m lambda curve for this Earth. Okay. And it is measured at 300 Kelvin. Okay, now we will have discussion on this plot. Do you have any query? So based on two fundamental radiation laws, so we have seen that how the energy vary with respect to wavelength as well as with respect to temperature. Okay. So take your time, just to review the discussion, just go through that once again, and I will again resume in 3 minutes. Okay, so is there any query related to the discussion we had recently? Okay, I have a query. Do we have a radiated component from Earth's surface at 1 micrometer? Query is, we have a sensor. Let me further explain this problem. A satellite-based sensor looking to a satellite-based sensor is looking towards Earth's surface, okay, and this sensor is designed at a sensor frequency of 1 micrometer, okay, having bandwidth 1.5 micrometer. So it means you can say that 1 micrometer is a central frequency. So it will be from 0.3 micrometer to 1 let's say it will go 1.5. So at center we have 1 and 0.35 you can write. .25 it should be. So this is the bandwidth, and it is at 1 micrometer center and total bandwidth 1.5 micrometer. So the half will be 0.75 micrometer. Okay, so it will start from 0.25 micrometer till it will be 7.5 micrometer. Okay, so the range in which this sensor is designed is 0.25 micrometer to 1.75 micrometer. Okay, and somewhere here you can analyze on this plot over here. So it is vary from 0.25 and let's say it will go till 1.7. So we do not select, generally we do not select such large bandwidth, but I have taken it for example. Okay, so this is the range in which this sensor is designed. Okay. And let's say when the sensor looks towards Earth's surface, as I said before, it virtually divides the Earth's surface into square blocks, where this is the smallest area element, and they are divided. That area is divided into grid. Okay, and one grid we call a smallest area element. So all grids are connected together. See, and each grid energy, like let's say in this particular grid, it is characterized on the basis of size. So let's say the side length, it is 2 meter. Okay, it's, you can say the one grid is 2 meter by 2 meter if it is a square in shape. So size is 2 meter, shape is square. Similarly, all grids are having the same shape and same size. and the total energy which is coming out, like again if I discuss that part over here, so what happened, let's say assume this is the location of sun, this is the entire electromagnetic radiation in which the energy is coming. Okay, so it finally interact over here at all points within this area, and it reflect and it will fall over here in the field of view of this sensor. Okay, do we have a radiated component over here? This is the query. If let's say this problem will be given in your examination, how will you attempt? We already have enough discussion on this.
Sir, radiation will be depend upon the object available on the Earth's surface, which we are looking for that. So if vegetation is there, then our reflection will be different. If water is there, then it will be absorbed, sir. As per the vegetation in NIR region, suppose.
Fine, you are correct. We'll come back to that discussion, like what is the capability. We analyze the this characteristic of material, how it reflects the energy with respect to wavelength. Here the query is like when the in the electromagnetic spectrum, energy components interact in the form of incident energy, it interact with all the points. Okay, so obviously there will be reflection takes place. So we have I'm not talking about the reflected component, I am talking about total energy which is coming out from this grid, and it is falling in the field of view of this sensor over here. So what is the composition of that energy? Does the energy contain the radiated component? This is the query. Because already 2 and 3 times I have discussed about this fundamental, this basic concept, like where we bifurcate the radiated and reflected component, etc. I'm giving you 2 to 3 minutes time, think it, then again I will come back. And I will ask anyone of you.
Excuse me, sir. Sir,
Yes, tell me.
sir, your question is that the sensors will detect it or not? Is this a question only?
Pardon?
Sir, your question is that the sensor will detect or
Could
not?
you please
Is this
ask
only
again?
your question? Sir, I'm asking that your question is the sensors will
Your
detect
voice is
the.
breaking.
So is it now okay, sir?
Still, I can't hear you very clearly. You can write your
Sir,
query in chat. I will read from there. Again, write your query in chat. I can't hear. I will respond.
So,
Yes, tell me.
so sensor will detect a very small amount of energy resulted in lower spatial resolution of the area.
See, I'm not asking about spatial resolution. Okay. The query is related to the energy composition from this particular area element, 2 meter by 2 meter. Okay. The energy which is outgoing from the surface area in the field of view of this sensor. Okay. So that is reflected energy or it is radiated energy. Both component will be there, reflected plus radiated both.
Sir, when the light energy is emitted from the sun onto the earth's surface, both the components of a radiated and reflected energy will be the outgoing components from all the features like trees, buildings and all that present on the earth's surface. Both reflected and radiated components will be present and they are sensed by the sensors and by the satellites for further processing of geo-information in the form of pixels representation. Sir, am I audible?
Sumit, could you respond?
Sir, am I
Yeah.
audible?
Yeah, you audible.
Yes, sir.
Yeah, Sumit, wait. Yeah, please continue.
Sir, whenever the energy is emitted from the sun onto the Earth's surface, the outgoing components from the Earth's surface will consist of both the components that are reflected and radiated. These two components, reflected and radiated, further get sensed by the sensors and get
Okay.
processed in the form of
Please,
pixels representation.
Yes, correct. Please wait.
Sir,
Just, am I audible to you?
yes,
Yes,
sir.
sir.
Okay. See
Sir,
over here.
every object, actually, sir, every object reflect according to its albedo.
That is fine. There is a reflected component. But you mean to say that out of three options, like radiated, only reflected, radiated, and reflected both, you select third option, is it?
Yes, sir. Both reflected and radiated components get be the outgoing from the Earth's surface.
Okay, let me further discuss about it. Okay, so just be on the unmuted mode. Just
Okay.
see, this particular sensor is designed in 2.5 micrometer to 1.75 micrometer. Fine.
Yes, sir.
Within this spectrum, 0.25 micrometer to 1.75 micrometer, just see this curve. Do we have a radiated component from Earth?
No,
No,
sir.
sir.
So if we don't have a radiated,
Sir, may I say something?
Okay, please continue.
Sir, when sun's rays comes, it comes in a small wavelength, and when Earth radiates the radiations, then it gets in large wavelength. So the reflected part is much more absorbed by sensors.
No, correct. Let me further end your discussion. You told that Earth absorbs the energy at low wavelength while it radiates the energy at high wavelength. Okay, so this can be clearly
Yes, sir.
visible from the 2D plot over here. Just see, within this spectrum, within this band, the maximum energy is there on the Earth's surface, fine, and it is a lower wavelength corresponding to this. What does this mean? Like Earth radiate and even the sun radiate, and even the Earth receive the maximum energy around 0.48 micrometer, as we computed earlier, while it radiate the maximum energy at 9.7 micrometer. So that is the meaning of your statement, like Earth absorb energy at low wavelength while it transmit energy at longer wavelength, correct?
Yes, sir. So large wavelength will contain the less energy, and small wavelength will contain the high energy. So the sensors will detect more the low wavelength energy content.
No, again, don't confuse me. This will be true if we do the independent analysis of either radiated or either reflected component. Fine. If we consider only the radiated component, okay, so just see in the radiated component, this plot will govern the way the energy is changing with respect to wavelength. It will be there. See, still we are not considering over here the reflectance, the reflectivity of material. That will be with the reflected energy component. So let me further explain about it.
Sir, may I say something?
Yeah, please continue in one go. Then I will take up.
Yes, sir. When radiations energy get reflected, then it gets reflected in the form it was radiated by the sun. But when it gets radiated, it gets radiated in the form it is absorbed by the Earth, means in large wavelength. And when reflected, then that's in small wavelength.
See, once the energy component is reflected back, the wavelength will not change. That is fine. But when it will be radiated, then this curve will apply.
Yes, sir.
You are correct. we have a radiated strong, we can say strong in the sense of the amplitude of radiated energy. It will be large in longer wavelength. And it is clearly, I think, I mean, visible over here on this plot. Okay. So this query I ask in the form of MCQ, where the first option is reflected, then radiated, then both 1 and 2, and none of these. Okay. So the correct option is reflected. Why it is so? Just see. The sensor is designed within 0.2 micrometer to 1.75 micrometer. What does this mean? It means the sensor only allow energy to be sensed within this spectrum, 0.25 to 1.75 micrometer. Now, to rule out whether it is, do we have a radiated component, what you need to see? You need to just see that whether Earth radiate energy in this wavelength, in this bandwidth. So in this range of
No, sir.
wavelength, Earth doesn't radiate. There is a 3 micrometer dividing line, as we discussed earlier also. Okay. So this is 3 micrometer dividing line, after which wavelength more than 3 micrometer, Earth starts radiating the energy. Okay. And the radiated energy keeps on increasing till 9.7 micrometer. So we'll achieve the peak at 9.7, and further with the increase in wavelength, it will decline, and further at around 50 micrometer, it will be 0. So we have the available radiated component only between 3 micrometer to 50 micrometer, where peak will get at 9.7. Got it? So let's say if I will change this range, sensor is somewhere in thermal band. Okay. And one more part over here, this I'm talking about this, if this is a reflected component, so reflected component will not be same as whatever the energy Earth radiate, sorry, sun radiate. 0.25 to 1.75 micrometer, if you plot this boundary, then let's say it is 0.25 somewhere lie over here, and it is 1.75 will go somewhere here. So this range, wavelength range, we are considering, and within this range, the reflected energy will be sensed, correct? Now, through this plot, we can say that this arc will tell you the radiated component from the sun. Okay. Now this particular magnitude, okay, along this arc, this energy will enter in the Earth atmosphere, but some of the energy will be trapped in the atmosphere. So it will further decrease. Okay. In the same arc, this range of energy within this 0.25 to 1.75 micrometer, it will further reflected back. Okay. So while reflecting back, some part of energy will be absorbed. So again, it will be lower than this. So the reflected energy, and finally the energy will be reaches to the sensor over here. So energy will be reaches to the sensor will be less than the energy that is radiated from the sun. And this is the reason why we need to do the study, what happens in the atmosphere, what happens at the Earth's surface, etc. Correct? So the reflected energy at the sensor will be less than the energy that is, we can say, the outgoing energy, because some part of energy will be absorbed in the atmosphere. So now it is clear in this. But if let's say if we design the sensor at let's say 5.3 micrometer, sensor is designed at 5.3 micrometer, then what will be the correct option out of these four?
Radiation only.
Sir, third one.
Hmm?
Sir, third. Both 1 and 2.
How many of you in favor of third, both reflected and radiated at 5.3 micrometer?
Yes, a third one.
Only second, sir.
Third one.
Third one.
Both 1 and 2.
Yani third option. Both 1 and 2 means third option.
Yes, sir.
Yes, sir.
Any one of you, none of these? Both option? Okay. The third option is correct. See, it's a simple problem of mathematics. 5.3 micrometer, let's say it is from range is 5.1 to 5.4. 5.5, let's say. So in this case, bandwidth will be 0.6 micrometer, 0.4 micrometer. If I write over here, okay. So 5.1 to 5.5 micrometer is the bandwidth of that spectral band, and that spectral band is centered at 5.3 micrometer. Okay. And you need to just check that you have idea about this plot. Okay. So what you need to do? Just draw two lines at 5.1 micrometer and 5.5 micrometer. So somewhere here, let's say this is 5.1, somewhere this is 5.5. Just draw two lines over here. And just see, do we have a radiated from sun and earth? So we have a both component lying between 5.1 to 5.5, radiated from sun and radiated from earth. But we need to ensure the availability of radiated component of sun at the sensor. Because see, this component will go to the earth atmosphere, there will be the losses. Okay, there we define whether atmospheric medium is behaving as an opaque or transparent medium for this. Okay, if this range is completely blocked in the atmosphere, it means you can't get the reflected component. But let's say if 60% out of this 60% energy is allowed by the atmosphere to pass through, then again it will reaches to this over here. Okay, and now again you need to ensure that whether in this range 5.1 to 5.5 there is a reflected component or not, and it will be decided on the basis of what are the material within this grid. If you get a significant reflected energy over here, then again it will goes to the same atmosphere and reaches to the sensor. Fine. As well as you have the radiated component. So you can say that both there is a possibility of both. There is a possibility there will be the radiated component, and there is a possibility of reflected component. With the comment like atmosphere allow this range of wavelength to pass through, and the material which are there in this grid, they have a significant reflectance in this particular spectral band. So if I will add in place of none of these, I will add one more option over here. the radiated plus reflected in case of atmosphere allow to pass through, and there is a reflected significant reflectance from the material. It can be written, and I will discuss it later on also. Just I am giving you the background over here. It's kind of legwork over here, so that to that fundamentals and basics, it will be further. Our discussion will be in detail later on. So the fourth option could be radiated will be there, and if let's say they will select the most appropriate option, if this will be the query, radiated and reflected, mentioning that the atmospheric transmission T, that is, let's say it is somewhere 0.5, and the reflectance of material overall in that particular field, it is, let's say, 0.6. So I can't fix it 0.6, on an average 0.6. Okay, in that case, there you can be say that with surety, like in this case, the sensor can get the reflected energy component, because 50% of energy is allowed by the atmosphere within this range. Okay, so it is 0.5, and 60% of energy that is interacting with the earth material is reflected back. So obviously they will go to the sensor field of view. Is it correct? So this discussion we'll do later on. What do we mean by atmospheric transmission T, and what is a reflectance rho over here, which characterize the property of material or surface material. Okay. Is there any query, or do you have any further suggestion or comment on this graph? If you can able to draw some more conclusion, you can share with me.
Sir, 3 mu micron is the point where reflection will become, I think, 0, and from there radiation will start. So how
No. Listen.
Sir.
Why reflection is 0 after 3 micrometer? See, Earth starts radiating the energy, it doesn't mean that it will not reflect back. Reflection will be 0 at a particular wavelength, when at that wavelength there will not be the incident energy, EI. Just see. I will further clarify your point. EI is the incident energy, okay, and here we have the radiated plus absorbed. To analyze the incident energy, what we are considering range 5.1 micrometer to 5.5, correct? This range we are considering only. As I said before, EI is we can also write it as a spectral composition. So just see that, do we have an incident energy on the Earth's surface in the range of 5.1 to 5.5 micrometer? Yes or no?
Yes, sir.
Okay, and that is the range. This way, I'm just putting my pen on the particular section. Can you see that?
Yes.
So this is the range. Just see, this is on the wavelength axis, this is a 5.1 and this is, let's say, 5.5. Okay. So in this range, we have the energy component from the earth, from the sun. Now when we have the, just what we need to do, just we need to ensure that the incident EI, if it is from sun, just see that. If I write EI from sun means amount of energy that is radiated from sun, it goes to the medium. So if I can write it, passes through medium. What happened when this EI energy within the range 5.1 to 5.5 micrometer passes through the medium, medium will absorb some part of energy. Okay. If let's say absorption is complete 100% energy is absorbed, then in that case, if I write over here in this particular range 5.1 to 5.5 micrometer, EI at earth, what it will be? It will be equal to 0. This will only happen is equal to 0 when atmosphere completely absorbs the energy. It is not allowing the energy to pass through. But generally, if you see that 5.1 to 5.5 micrometer, we'll see that later. This will not be completely blocked. So let's say if some part of energy is absorbed in the atmosphere and remaining part reaches to the Earth's surface. Correct? So still, just see, this composition will not change. Again, okay, the part which is reaches to the Earth's surface, it is only within 5.1 to 5.5 micrometer. Correct? But the strength EI, if you multiply by factor alpha over here, generally we multiply it by T. T is less than 1. T is less than 1. So with T factor, this energy will decrease, correct? Yes. Now what happened? This TEI interact with the Earth surface material and we have a reflected component ER over here. Okay, so ER, now this EI you should write TI because at the Earth surface point we are applying the law of conservation of energy. So T into EI is equal to ER plus EA. Now this ER depend on material property. Okay. How much amount of energy T into EI is reflected back from material. Correct? Again, the spectral composition will not change. The reflected energy component will be again in the same range, 5.1 to 5.5 micrometer. Always remember, the reflected component, if you measure at a particular wavelength, let's say lambda is equal to 5.3 micrometer. You measure at this, okay? So incident will be also measured at same wavelength and reflected. It means the reflected, if you analyze the reflected energy, the wavelength will not change, like in the radiated. In the radiated, we say that like at a shorter wavelength, energy is absorbed, but it is radiated at longer wavelength. It is not true over here in case of radiated component. You measure the radiated EI at 5.3 and you also measure the reflected component at 5.3. Got it? Yeah. So again, let me finish. Let me conclude. Yeah. Okay, still some part is left. So the radiated component will again be in the same range. Just see on this 2D diagram, 5.1 to 5.5 micrometer. Correct? And if material reflects significantly, then that reflected energy will be there. along with this radiated component. Okay, and they will reach to this energy will reaches to the field of view of the sensor, and it will further sensed, and equivalent DN number will be assigned to this particular grid. Okay, thanks for pointing out this part, due to which we could do the detailed analysis on this. Even I would like you to just ask participants in the discussion. Don't think that your query could be not in the right direction, or it could not be the proper query. You could not respond it correctly. It's okay.
Yes, sir.
Just contribute in the discussion. Whatever conclusion you have, it will be further discussed with us, among all of us.
Thank you.
You're welcome. I again say that a lot of analysis I'm combining in my discussion. So that's why I told that the way I'm writing on the screen, you need to make note on that. So you will have a recorded video with you, but still if you are writing with me, then it will be easy for you later on for the revision. If there is any other point or any conclusion, if you feel that that can be derived based on this plot, that is a spectral radiant exitance curve of Sun and Earth, so you can share with us.